I would like to introduce, most of it certainly, I've never met the gentleman before, I would like to introduce Mr. Greg Nutt, who kicked this whole damn thing off. So, Greg.
Thank you. So I decided to talk about where NuttX came from, kind of thinking that the processes that I went through before I created the operating system, and the kind of problems I was trying to solve. So I call this thing beginnings. But in order to talk about that, I have to talk a little bit about myself. So essentially my career, I divided it into four pieces. There's the time I spent in university, which was about 10 years. I never had any plans to ever have a job. I had always intended to be a professional student. I had fellowships that paid everything for me. So, I just studied whatever I wanted to. It took a long time to get my bachelor's degree, for example. By the time I decided to get one, I had enough credits for a double major and all the coursework for degrees in mathematics and physics and psychology. So I picked two, and I picked psychology and mathematics. Because I had this career goal at that time, not a career goal, but this interest that I wanted. I was very confident when I was young, not so confident anymore. But I believed that I had these math skills that I could understand how brains worked. So I actually went to graduate school and studied neuroscience for 4 years in a PhD program in Michigan. Most of the coursework I did there was actually digital signal processing. I was interested in stochastic processes when I was a math major, and I did most of my work in digital signal processing and brains. And I had my thesis, my PhD had to do with recording from neurons in the brain and in the eyes of cats, and using Wiener filters to understand how the activity in the eye affects your brain. I actually thought I could explain all this. But in around 1978, something happened. I had 2 kids. That happened. And another guy duplicated my experiment, my thesis. So kind of took the wind out of it. So at that time I looked around and said, I got to get a job, because I'm living in a mobile home with a wife and 2 kids, living on a fellowship. So I looked around at my skills and said, what can I do? Well, I got some mathematics, I got some signal processing. This stuff's probably not much use, and I spent a lot of time doing assembly language programming, which I'll talk about in a minute, when I was a graduate student. So I ended up with a job at a company called Sanders Associates, which is the green stuff here, military stuff. So I was doing signal surveillance and electronic warfare, anti-submarine warfare, lots of direction finding, lots of spooky military stuff. And that's where the first multitasking operating system was created for those products. And later I went into the commercial electronics at HP, and I had the opportunity to write the operating system for the Hewlett-Packard LaserJet printers, which is really a direct descendant of NuttX. I mean, it's like, I didn't take the code, obviously, but the design is the same as this. This operating system, this, and NuttX, same basic underlying concepts. Okay. In recent years, since 2000, I've only done open source software. I created a small business called RidgeRun that did Linux board support packages. And I had this company for a while, but I'm fully retired now. So that's all history. That's where it came from. So when I was in graduate school, these are the computers I was using. So this is where I did most of the work, that picture. That's not me. So we were talking about this last night. So this one, and this one, all had several hundred boards, each with one transistor on it and each implementing one gate. So you'd have NAND boards and NOR boards, and OR boards, and you connect all these boards. This big thing, that's the back plane there. It's just spaghetti hanging down. And that was plug in instructions in the front panel, DEC drives. DEC actually got its start doing these things as kits in 1962, I believe. And I also had my home computer. So I was doing some Z80 civilian language programming. When I went into the world of military, this is the first operating system was built on this creature, which was a bit slice. AMD used to be very popular in the early 80s, late 70s, to purchase AMD bit slice parts. Get a whole bunch of them, stack them up, you get a 16-bit processor, control some microcode, and you got a computer. So the company I worked for designed this thing, ran it 5 megahertz, 16-bit. It actually had a pretty nice architecture. It was 16 general purpose registers. The architecture is pretty contemporary. Not RISC, of course, it's just microcoding. So the first operating system, I don't know if you call this an operating system, you probably think of more as bare metal programming. But basically, whatever you're doing is an operating system. I mean, unless you're just writing straight line code, it's an operating system, right? So the simplest thing you do, and I think we've all done this at some point, is basically you just have a bunch of interrupts. Every interrupt, when an interrupt occurs, you do something. And you have to do it all the way to the end, then you're done. And you wait for the next interrupt. Actually, this works great on small systems. If you're working with an atmel part or some AVR part of some kind, this is a great way to do it. You probably shouldn't put an RTOS on it. So what's wrong with this? Well, back in those days, most processors didn't have prioritized interrupts. So what's wrong with it? Well, if you want deterministic behavior, then that's the interrupts is going to affect the response time. You can control that, so it's not really a problem. You can probably meet all your deadlines with some variability. What other problems are there with that? First of all, I think this is a pretty good solution for really limited resources. But you can lose interrupts. If this interrupt extends too long, you might lose an interrupt. Maybe. But I think the main problem with just using interrupts to run a system is it doesn't support any kind of waiting. Everything has to run to completion, right? So normally these things also include some kind of loop running in the background, right? So it does A, B, C, D, E, F, G, A, B, C, D, E, F, G. So what's wrong with that? That's not deterministic. Suppose I'm doing task C, then something I have to do for task B happens. It doesn't occur until I go all the way around the loop, right? So the time to processing is random, basically. You don't know when it's going to actually occur. It's like Windows. So when we talk about real-time systems, we talk about them behaving deterministically. What we mean by deterministic is that there's some kind of stimulus, there's a latency, then we make the response. And that response always has to occur before the deadline. So if you're doing electronic warfare, for example, and you're sampling pulses from radar, your job is to put a cover pulse on every pulse coming out of the radar, back in those days, when radars were easy. Obviously, if you fail your deadline, you just expose an aircraft to the threat, right? So it's very important to always complete the computations before the deadline. But it's important, real time doesn't mean fast. A lot of people, for example, real-time Linux, RT Linux, it's real time, it's just not fast. It depends, there's more things to talk about. But. So some of the problems with operating system number 1, that is the interrupts taking too long, can be solved by just putting a queue, right? So the interrupt occurs, now it's very brief, because all it does is queue some work. Then the work happens back in the background loop. Of course, it's still not deterministic because you still may have to go all the way around the loop before you can process the response. Not deterministic, but it's better in some ways. So one thing that people do, I've done it, I'm sure some of you have too. If you're running a little main loop and you want to get back around the loop fast, is you break each of the things you have to do into pieces. So you put a state machine in every one of them. So now you have a loop of state machines. Each of them goes through and says, oh, I got to do something. I'll start it now, then I'll just exit. The next time I'll come around the loop, then I'll do a little more, then I'll exit. Then I'll go around the loop a little more, and finally I'll finish it. So, first of all, it's really dumb. It just looks really, the code looks really bad. And you have these spurious state machines in every task. The code is just awful. It's still not deterministic. We didn't eliminate the delays, we just made them smaller. What you want to do is eliminate them as much as possible. So when I first came to HP after doing operating systems in the military work, this is kind of a summary of what the original LaserJet operating system was like. There was a background main loop and a foreground one with one context switch. So if something important happened while you're running the background loop, you could do it in the foreground loop. It's better. But it's still not deterministic because it's still running in loops, right? And the looping is the problem. So the operating system that I did originally back in the 1981, 82 was more of a contemporary. This is kind of a contemporary picture of any RTOS you might want to see. So now tasks, when they start, they can be ready to run. The highest priority one is the one that's actually running, right? So this is fully prioritized, strictly prioritized. A running task, for example, two things might happen to a running task. Some other task of higher priority may need to run. So the running task goes back to ready to run, but not running. Another thing that the running task can do is it can say, oh, I need to wait for a resource. So I'll take a semaphore. Oh, I got blocked. So it might go to a block state waiting for a semaphore or a message or something. At some time it fulfills, it gets the resource, it can continue running, goes back to the ready to run state. If it's the highest priority, it gets to run again. So the original one from the 80s had these three states. NuttX has an extra state over here. That's to support disabling preemption. So the way, if you want to disable preemption, the way that works is when the task is blocked, it says, oh, I'm ready to run. You don't get to go there because preemption's disabled. So you go here. When preemption's re-enabled, then you get back. Okay? So I need to talk about the deck connection. This was done in New Hampshire, and just down the street was another business called Digital Equipment Corporation, which was really, really big. I miss them. It's sad to see them go. But they used to exchange a lot of employees. You get tired of working for the company I was working for, you go to work at DEC. DEC guys that get tired of doing that, they'd come to work. It's called Sanders. Come to work for Sanders. Which is really kind of funny because they do spooky military work, but now they're owned by a British company doing spooky work for the US government. And they can't tell their managers about their projects. I don't know how they manage them. I heard that from people that still work there. And so we talk about how this stuff is implemented. So that's the secret that makes it deterministic, or nearly deterministic. You can't really achieve true determinism, but you can get close. These switches between states happen by a context switch. A context switch is, think of long jump and set jump. You call long jump at one place, it says, if they ever call, we call set jump. We call set jump in one place, anything below it, if it ever wants to, we can call long jump and come right back to that same place, right? with the stack just the way it was, everything, all the registers, just the way it was. Context switch then is just a set jump and long jump on steroids. Because not only does it remember just this easy stuff like return address and some things, but it has to remember the whole state of the processor. Okay? And these get represented by data structures called task control blocks. And these are hooked into lists. So each of these is really a list. There are multiple block lists. But essentially, if you want to know the state of a task, you say, what list is it in? Okay. So in RTOS now, so I probably should mention that, so the time you get from one state to another, that is a fixed time. It's that context switch time. It's not a random time, it's a fixed time. So interrupt processing under an RTOS, this is any RTOS, not just not any RTOS. There will be an interrupt handler. It should do as minimal amount of work as possible. It should just start a task, say, okay, here's the interrupt, an event occurred, run the task that corresponds to it. So NuttX is very highly optimized, so the context switch in that circumstances is zero overhead. You go from the interrupt handler event, when the interrupt returns, you go directly to the task that processes the interrupt. So I think I just said all of those things. I said all these things too. The interrupt, minimal amount of work, very small. So a lot of things that come up is all modern processors support prioritized interrupts. But what's the value of prioritized interrupts if you're following a good RTOS model? It's not really, no real significant value to nested interrupts, prioritized nested interrupts, if you're following this model. Because you only need priorities on interrupts if your interrupt handling is long. So NuttX also supports symmetric multiprocessing, which I hope other people are going to talk more about that. I'm not going to say much now. But essentially, it's the same basic state machine, except for there's many, many things running. Depending on the number, if you have n CPUs, there's n tasks running at once, all at the same time. Of course, I've simplified this to some other data structures, but this is basically SMP. And you get this additional concept of spin locks, so that since semaphores don't work across processes, I mean, you can't just lock something by the mutex. You have to also stop the other processor. So spin lock is just what it says. It's a loop on self and until I can continue. Okay. So how do I know that just having prioritized tasks and fixed context switching times is going to give me real-time behavior? Well, there's lots of scheduling algorithms. Probably the oldest is rate monotonic scheduling. So it's guaranteed to meet a deadline. It doesn't tell you what the deadline it's going to meet is, but it's guaranteed that your system will always meet a deadline, provided you follow some simple rules. Those rules are strict priority scheduling. Don't have two tasks running at the same priority. All tasks should have its own unique priority. Priority should be static. Don't reprioritize things. And you have to assign the priorities according to rate monotonic conventions. That is, the tasks that have the shortest response latency are the highest priority. Now we always have a temptation when making a product. We have this one feature that's really important. And we want to make it the highest priority. But sometimes that's not the best decision. Maybe it doesn't have to be the highest priority. The highest priority should always be the one with the shortest response deadline requirement. But of course, it also has this other assumption which is completely unrealistic. In the real world, you can't do these things. This breaks the real-time processing. You can't share resources. Well, of course we have to share resources. If you share any resources, then you have to lock them, right? And if you lock resources, then you disturb the the ordering and prioritization of tasks. So no semaphores, no locks, no critical sections, no disabling interrupts. Well, of course, we're going to do all those things. But if you design your system right, you should manage those things and make sure they aren't. So every time you do one of those things, the interrupt time, instead of being an absolute deterministic time, will become a variable time around that. You can handle those things. And there are also, Dave and I went through a bunch of these things with the NuttX RT, as he found some semaphores were being held too long and were causing jitter in some responses. And the solution is don't do that, right? But the important thing is finding out who's doing it, and why they're doing it, how long it takes us, and how you fix it. And we work through some of those kinds of things. We put some tools, and NuttX has a pseudo file system, for example, so we can keep track of the latency of all responses, of how long the tasks are disabling interrupts, how long tasks are doing these bad things. They're not bad, we have to do them, they're important. They do affect real-time behavior.
So how do you do scheduling decisions for hard real-time systems in practice then?
I'm having trouble hearing.
We have a microphone, that's probably the easiest thing. Give me the...
Can everybody hear okay?
Yeah.
Yeah.
Looks good.
All we have to do now is figure out the technique.
So, yes, that is working.
Probably want to be about there.
Okay. So my question was, if rate monotonic scheduling does make unrealistic assumptions, what do you do in practice when you have to design a hard real-time system?
So what you would do is you would actually measure the performance
Okay.
of all your tasks. It would be nice to have. It would really be great to have some external tools that would show you nice graphics. But what we have right now for measuring that is. So I mentioned that NuttX supports a pseudo file system. Looks like the /proc or /sys in Linux. It lets you look inside the operating system and see what's going on. So we keep track of all these things in the operating system. So if you enable that feature, you can look at this file and you can see what tasks are holding semaphores, or what tasks are keeping preemption locked, or keeping interrupts disabled, and for how long. And when you see a culprit in there, you see somebody who's disabling interrupts for a long period of time, you say, well, go redesign that little piece of code that's doing that. Don't do that. You can, for example, if it's disabling interrupts, you can usually break that into several pieces. So it's not important what percentage of time you disable interrupts. It's really irrelevant. What's important is how long you disable interrupts. You can have interrupts disabled 99% of the time, but if they're enabled periodically so that the absolute time the interrupts are disabled is short, then you still have good real-time response. It's not about how long interrupts are disabled. It's not about how percentage of time interrupts are disabled. It's about the maximum time they're disabled. So everything I've set up till now, you can probably say about any other RTOS. All the slides probably could apply to free RTOS or GVR OS or most any of those. So what really makes NuttX different, I think, than every other RTOS you'll see out there is its strict conformance to POSIX, the POSIX interface. As opposed to other operating systems have a scheduler and a hardware abstraction layer. NuttX has a pure POSIX interface with the POSIX device driver interface. So why? Well, real reason why is because when I worked at HP, I had several reasons. I was the overall architect for the HP firmware, but I also had responsibility in particular for the operating system and for interfacing with third-party solutions. Like back in the days when you wanted PostScript, you put a SIM card with PostScript in it. So those had to follow strict interfacing rules. So I was very much a modularity, interface, standardization guy. So when I produced the kind of operating system that I wanted to use, I wanted to follow all those kind of things. I wanted an operating system that's portable. In theory, you could take any piece of Linux software and run it on NuttX, provided it doesn't draw in too many other libraries that you don't want, and provided it follows the POSIX standard. So at this point, I think it's also the identity of NuttX, strict POSIX compliance, and so I don't think it's a. Another thing that this POSIX interface layer gives us is the ability to build in other configurations. Because each of the POSIX interfaces gets, in a flat build, like your normal processor, that is all the memory just is lined up. You see all the memory, and it's all the same everywhere. It's homogeneous. There's no special regions in memory. That's the way most people build the operating system, right? But other modes, for example, you might want to say, this is a user sandbox. The user can only work in this area. The user sandbox, the user can only work in this area, and I have this protected area where I have my operating system and my special recipe secret code that I want people poking around in. Or maybe I'm running an interpreter or something. I don't want the interpreter to be able to access stuff in the code. So in that case, a protected build gives you that advantage. But a protected build now, to get from user mode, if you want to call it the operating system, to get from user mode back into supervisor mode, you have to go through a call gate. A call gate is a special function call that not only does the call, but also changes your privileges to supervisor mode. So those interfaces, because we're following POSIX, those interfaces are all carefully controlled. So nobody can call into the system without NuttX being in control of the call. So that allows us to have protected builds. NuttX also supports kernel builds on systems that have MMUs. A kernel build is just like Linux. Monolithic kernel module, a blob, and separate blobs, separately built blobs for every process. Tasks become processes when they're enclosed in an address space. Okay? So, I'm really done, but I just want to follow up on a couple of things. One thing that's in NuttX that's a really important piece is that interrupts, to keep interrupts very brief, they're divided into an upper half. The upper half is what you actually do inside the interrupt handler, and a lower half. So the top half, upper half, does a prioritized work queue, and there's something called a work thread that runs. So this picture should look familiar because you can see that it's basically the old main loop. So it's not deterministic. People should be very careful using the high priority work queue. I know from discussions I've had people have overused it. It's intended to be available all the time just for back-end interrupt processing. Okay? Just kind of a warning. And how do you work around that is NuttX supports prioritized work queues as well. It supports a high priority work queue which should be dedicated just for interrupt back-end processing. Then multiple low priority work queues that live in a thread pool. A thread pool is like I always think of it as like a little corral full of little ponies, right? And when I want to go for a ride, I take one little pony out, go for a ride on my little pony. So you can configure how many ponies there are, and when something needs to be done, you can take one out of the corral. Make sense? That's it. I didn't think you have a last slide saying the end. That's it.
Questions?
Yeah, I can be loud. So what's the difference between the top half and the bottom half? Are interrupts back on again in the bottom half?
Bottom half is just a regular task,
Okay,
but it's very high priority.
I see. So,
So,
it's got,
so the interrupt occurs and the high priority work will run immediately. So the context switches are highly optimized in that case. So when you return from the interrupt, it will vector to that high priority processing with zero latency. No context switching over.
and interrupts are back on again, aren't
Yes.
they? Yeah, that's what I thought you meant. Okay.
So essentially, you took the interrupt and you said, immediately deferred it back to a non-interruptible,
Yeah.
back to an interruptible state.
Okay.
That allows you to take the next interrupt essentially immediately.
Can I follow up with another question?
Sure.
When you're doing things like spin locks on multiple processors, have you ever experimented with using something like Peterson's algorithm to do, strict alternation but non-blocking?
No. No, all the stream locks are. So normally, so there's lots of ways you can ruin real-time performance, like round-robin scheduling, for example, ruins performance. So normally to get real-time performance, you have to think of everything having strict priorities and runs to completion at its priority level. So anything to me that I don't know very much about this particular algorithm.
Oh, okay.
But in general, my first impulse is that anything that's time sharing, time slicing, won't be real time.
It's not really a time slicing thing. It's a way when two people are trying to get access to something, one guy gets it, and then the next guy will get in the next time, and rather than in a spin loop, it's kind of random who's going to get the next time. It's like one guy could starve out the other, for example.
I haven't looked at that.
Yeah, okay.
We're going to have, hopefully, plenty of time in open sessions, breakout sessions, and so on. And these are exactly the kinds of discussions that we should have there, because you're going to need whiteboard, you're going to need bits of paper, and just being able to stimulate each other with things to look at and things to consider that we haven't, we all come from different backgrounds, will be really interesting. But let's take some of these things and...
This is actually a better question for Ishikawa-san, because he knows much more about NuttX SMP than I do.
Yeah, so actually, tomorrow I will talk about my experience with that
Great.
SMP.
Cool.
Yeah.
Thank you very much, guys. I think you've set up quite a lot of the presentations which are following without actually necessarily realizing you were going to do it. So things like instrumentation and things like that, I think, are definitely going to come up over the next couple
I'd
of
love
days.
to see some good instrumentation tools like you would get with the commercial operating system.
Yeah. Okay. So, thank you very much.